Hey darts fans, that's Timo Newman here, the transporter. Welcome to the good ship Undarted Waters. This is the third video in this series, The Physics of Dart Flight. And that kind of sums up my darts right now, just kind of away from the camera. I'm going through a bit of a dodgy patch. So yeah, enough said about that. So we're back down to earth today because in the previous video we were looking at the flight, the trajectory of darts in outer space where there's no gravity and no air, just vacuum, and we showed from Newton's first law that darts travel in a straight line. Independent of the mass of the dart as well, by the way, they just travel in a straight line. So today we're coming back down to earth, but keep your oxygen mask on because we're not allowing air yet into this discussion. So we're pretending that we're in a vacuum on earth, okay? Because air resistance is quite a difficult topic and we're going to cover that in 2 videos time probably, but today it's all about gravity, and gravity is by far the most important force that we need to understand in order to get a handle on the trajectory of darts. So let me get my whiteboard and we'll talk about Newton's second law. So let's just do a really brief recap on Newton's first law. And let me just call that N1. And what Newton's first law basically says is that if the forces acting on an object are zero, then the velocity of that object will be constant. And as we saw last time, it's really important that when we say the word velocity, we bear in mind that that is 2 different things. It's the speed, which is the size of the velocity, but it's also the direction. So if something's moving at a certain speed in a certain direction and there are no forces acting on it, according to Newton's first law, it will just continue in that same direction at the same speed. So Newton's second law is all about, well, what happens if there is a force acting on an object? And Newton's second law says that if a force is acting on an object, let's say that I give this a push, it will respond to that force. And the way that Newton specified that, he said that if a force acts on an object, it accelerates, and the direction in which it accelerates is parallel to that force, is in the same direction as that applied force. So if I have a wheelbarrow at rest and I get hold of it and I start to push on it, the wheelbarrow will accelerate in the direction that I push on it. And the harder I push on it, the faster it will accelerate, okay? So Newton's second law then says that if the force is not zero, so if force is not zero, then the object accelerates so here's an object. I'm going to apply a force to it, and this object will, let's assume it was at rest initially. I apply a force to it, it's going to start accelerating. In the direction in which the force is applied, okay? Now, we don't have the same units for force as we do for acceleration. Acceleration is just the rate of change of velocity, so we measure it in meters per second, but force has different units to that. In modern units, they say that force has units of newtons, in honor of Isaac Newton. So we need a constant that relates the acceleration to the force. And what is that constant? It's the mass. It's the mass, okay? So if we want to make this law more precise, what we say is that force equals mass times acceleration. So if I apply the same force to that wheelbarrow, but it's twice as heavy, the acceleration will only be half as much, okay? Or, yeah, so if you double the mass of something but you apply the same force, then you get half the acceleration. If you lower the mass with the same force, you get more acceleration. And this is actually the definition of mass, comes from Newton's second law. The mass of something tells you what size of acceleration does it have from a given force, okay? So that's Newton's second law. Now that's quite abstract, but let's now apply it to our beloved darts, all right? Let's get rid of all of this. Because when we start talking about darts back on Earth, we need Newton's first law and we need Newton's second law. And why is that? It's because if we think of our dart in mid-flight, remember, if we ignore air resistance just for now, the only force acting on this dart is gravity, and gravity is trying to pull this dart to the center of the Earth. So basically, as far as we're concerned, the center of the Earth is right below us. So, you know, if I drop this pen, it's going to fall to the floor. I don't need to demonstrate that. The reason that I'm standing on the floor is because gravity is pulling me down to the center of the Earth. And luckily for me, I'm standing on some floorboards that are in a house that's built on some rock, and I'm not falling to the center of the Earth. Phew, thank goodness for that. So gravity acts in terms of our dart straight downwards. And now this is probably the most important moment of this entire series on the physics of dart flight. You now see the beauty of what we're doing when we say that the velocity as a vector has a vertical piece and a horizontal piece. So this dart here is moving in a certain direction. It's got this velocity. And remember, we say the velocity is a vector, so here's a velocity. It's got a horizontal piece and it's got a vertical piece. So we can call this V, let's call it V horizontal and V vertical. Okay. And we can treat them separately. That's what I was saying in the previous video. We can treat them separately. And what you'll see is, as far as the horizontal, what we call the component of the velocity is concerned, there's no force. There is no force because the force is acting due to gravity straight downwards. That means that this horizontal component of the velocity does not change. That's so important. It does not change. The force only is going to change the vertical velocity. Okay, and because it's going downwards, that means that if the vertical velocity is in an upward direction, it's experiencing a deceleration because the force is in the opposite direction, so it's going to slow down. And then as it comes down, it's going to experience an acceleration because now it's moving in the same direction as the force. Okay, so I happen to have a golf ball here, but if I throw this golf ball, you know, you see, obviously we all know this from experience, but it goes up, it slows down because it's decelerating, because it's basically being acted on in the opposite direction by gravity. It reaches its highest point, and then it starts to move down from rest, and it starts to accelerate. So in the vertical direction, all that's happening to our dart is that it's going to decelerate, and then it's going to accelerate. And in the horizontal direction, it's just going to move as if nothing's going on. And it's the combination of that, the constant horizontal motion, and the trivial decelerating up, accelerating down, the combination of those gives you the trajectory of a projectile. So let's just make a drawing of that. Okay. Let's just set up our friend really quickly here. So we've got our pal who is always smiling. There he is. His nose has got a little bit bigger. So he's throwing his dart. Over here is the dartboard. Okay. And we had all of these different parameters that we talked about, you know, the elbow height and all that stuff. And we can write that in a minute, but let's just get the physics sorted out here. So Charlie here is going to throw this dart, and we know the trajectory will look something like this, okay? But we can break that down into two pieces. The horizontal component of that initial velocity that he throws it is just going to stay the same if we ignore air resistance. So that horizontal component is like the horizontal ghost of the dart, if you like, is moving just in a straight horizontal line with a constant speed. And then the vertical piece, let's do that in a different color, is going to go up, it's going to slow down, it's going to come to rest, and then it's going to speed up again. Okay, and when you combine this constant motion in this direction with this decelerating, coming to rest, accelerating, you combine those, you get this beloved trajectory, which we recognize from all kinds of things in our lives, including lots of sports. We see the ball moving in this kind of trajectory. Okay, now if I throw this ball in the air and it comes back down again, it's symmetrical in the sense that when it hits my hand, it has the same velocity downward that it started off going upward. So it goes up, decelerates, and then comes back down again, and that's symmetrical. Like if I played that in reverse, it would look just the same. Okay, that motion. And what that means is, in the absence of air resistance, because this is a constant motion and this is a symmetrical motion, this shape, this parabola, is actually symmetrical. So let me try and draw it a bit more accurately as symmetrical. So what I mean is, if you take the midpoint between where you release it and the board, then that motion will be symmetrical on either side, okay? Like that. That's assuming here that the target is at the same height as where it's released, just that symmetry there, okay? And we have a name for that shape in mathematics and physics. That shape is called a parabola. So a parabola is what you get from throwing a dart in the absence of air resistance. Okay, that's a parabola. Now, someone left a really good comment on my previous video about darts in outer space. We were talking about the dart moving in a straight line, and they said, what about the weight of the dart? That's a good question. So you might say, well, hang on, Timo, what about the mass of the dart in all of this? And what's amazing is that it doesn't make any difference. So this shape is independent of the weight of the dart. Okay, I'm going to demonstrate that in a second. Let me just point out one very important sort of, not assumption, but one very important sort of statement connected with that. We are talking about a dart that's being released at a certain speed, u, all right? So the speed with which we release the dart is, we're going to assume that's the same for darts of different weights. What that means is that if I went, say, from a 20-gram dart to a Ryan Searle 32-gram dart, because the mass of the dart has gone up a fair amount, in order to deliver that dart with the same speed, I'm going to have to put a little bit more oomph into my throw. So I need a bigger impulse in my arm to get that, to get the Ryan Searle dart at the same speed as the lighter 20-gram dart. So when I say that the shape of the trajectory does not depend on the weight of the dart, that is true assuming that we release all these different weighted darts with the same speed. And all that means is we have to make sure that we give more energy to the throw in order for those darts to have the same initial speed at the very first instant they're released. Okay. Now most of the energy in our throw is actually in moving our arm, because our forearm and our hand weigh more than a dart. All right, so it's not like you have to double the energy of your throw in order to throw a dart that's twice as heavy. It's really a small percentage. It's really that you're trying to get that whole part of your limb and your hand moving at a certain speed. The dart's traveling with the hand, and when the hand releases, the dart just has then that velocity. It's like if you throw an apple out of a car window. In the car, the apple's moving, say, at 30 miles an hour with the car. When you throw it out the window, it's going to have that same initial motion, 30 miles an hour. Okay, so if there's a poor pedestrian nearby that gets hit in the face with an apple core, it's going to really hurt, because it's like someone threw it at them at 30 miles an hour. Okay, so let me just do a quick demonstration here about this, because this is something that many people do not have an intuition for, and really no one did up until Galileo. Generally, there's you know, if you asked people in the street about, you know, having a heavy object and a light object and dropping them, which hits the ground first, most people will say the heavier object hits the ground first. And this is a fallacy, actually. Okay. Now there is a little bit of a wrinkle here to do with air resistance, but if you were in a vacuum, certainly objects of all masses will hit the ground at the same time. Now I'm going to demonstrate this to you. I've got a ping pong ball here, and I've got a golf ball. Okay, don't know if you can hear the difference. That's the golf ball, that's the ping pong ball. Okay, I weighed these on a kitchen scale. This weighs, the golf ball weighs 47 grams and the ping pong ball weighs 3 grams. So this is 16 times heavier than this. But I'm going to drop them, hopefully just about perfectly at the same time, and we'll see how long it takes them to reach the ground. And I've got a separate camera here. I'm just going to turn it on. So I'm turning on this other camera that's pointed at the door here, and I'm going to just, this other camera now, bring these two balls into view. So the ping pong ball is this one, and the golf ball is this one. And I'm going to drop them at the same time. 1, 2, 3, go! And yeah, they hit the ground at the same time. Turn that other camera off. So this means that this trajectory in a vacuum for certain does not depend on the mass of the dart. The mass of the dart, though, will play a role when we deal with air resistance, and that's because the effect of air resistance will be more pronounced on a lighter object than it will a heavier object. All right, and that might lead to some counterintuitive things that we'll see as we go along. So I don't know if there's much more to say today than this, because I think I've got the key concepts across that I wanted to. What we're going to do in the next video is bring this physics to bear more precisely on the throwing of the dart, and we'll put back all those parameters that I talked about. And what we'll look at is, how does the angle of release of the dart and the initial speed of the dart, how must those be related in order to hit the target? Okay, because actually there was one last thing I wanted to say here. By splitting the motion into the horizontal and the vertical, there's a very easy thing that we can immediately get from this, which is how long does it take the dart to reach its target? Because all we need to know is the horizontal component of this, which we call V horizontal. Because this part doesn't change, we know this distance between where the dart's released and the board, which roughly speaking is the same as the elbow distance. There's a little bit of extra because of the forearm, but let's just ignore that for now. But basically, if something is moving over a distance d with this speed v horizontal, then the time it takes would just be the distance divided by the speed. Okay, so if you're traveling at 60 miles an hour and you've got a journey of 30 miles, the time it takes would be the distance divided by the speed. So 30 divided by 60 would be half an hour. Okay, so we can get the time of flight directly from knowing the horizontal component here. Okay, and the time of flight will be faster if this is bigger. So the time of flight will be shorter, I mean, if we increase the horizontal component. So a shallower dart, okay, will reach the board more quickly, which is kind of obvious, because if you have a dart that's pointed up very high, it has to go through a very long trajectory in order to reach the board. Okay, but this leads to a very interesting piece of physics here, which is really cute, which is that if you, let's say we keep the speed of the dart the same and we vary the angle, then if the angle basically is 90 degrees, so if this poor person doesn't know how to play darts and they just throw the dart vertically up in the air, boy, they better have a good hat on, right? Then the trajectory then would just be up and then down again. If they have an angle that's just a little bit less than 90 degrees, it would kind of look like this, the trajectory. Okay. On the other hand, if they throw the dart at a very shallow angle, the trajectory would look like this. Now, if you imagine these were like cannonballs and this is the Earth, then the very high sort of initial angle cannonballs don't go very far, and if you have a very shallow trajectory like this, that doesn't go very far either. And you can ask, well, what angle must I direct my dart or my cannonball to get the biggest range, okay, for a given amount of energy I put into the dart? So if I have all of these start with the same speed, here all of that speed's being invested in the vertical direction, here all of the speed's being invested in the horizontal direction, but there'll be an angle where I'm sharing that speed between the horizontal and the vertical to get the most range. Okay, and you can ask, well, what, that's going to be some kind of Goldilocks angle where I get the greatest range. Okay, and the answer is very simple. It's 45 degrees. It just comes out of the physics, you know. So 45 degrees is a very special angle in projectiles. That's kind of where, in the absence of air resistance, you get the biggest bang for the buck. You're perfectly balancing your vertical and horizontal components. If you have too much of the horizontal, the dart's just going to go, just going to fall off the cliff, as it were. If you have too much vertical, it's just not going to reach the target. And it turns out that 45 degrees in the absence of air resistance is the perfect amount. Okay, so I just want to kind of mention that right now, and that comes from the theory of projectiles. It's not going to be quite 45 degrees for us because we have this extra little wrinkle that as we change the angle, we change where we start the dart from. And that's why this becomes quite a tricky problem. But I won't give you all the technical details in the next video, but I will show you the results about what is that Goldilocks angle. Okay, and we'll start to see some very pretty things happen. And how does that Goldilocks angle depend on the target and also on your personal unique data, which is related to your stance and your action. And this is where all of this stuff starts to get really useful and interesting. So that's enough for today. I hope this has been useful for you. Some interesting physics, and you can see how it's going to start to really tell us a lot about the projectiles of our beloved darts. So with that, 3 darts at the Oki. I hope you're all doing well, and I'll see you next time.